Welcome back, podcast 15.2. We're going to do some examples now using our newfound tool, the ICE table. So example number 1, here's our equilibrium. Sulfur dioxide mixing with nitrogen dioxide comes to equilibrium and forms sulfur trioxide and nitrogen monoxide. And we have some initial concentrations, and we also have how many moles of NO is found at equilibrium. And our job is to determine the value of Kc. So let's go ahead and set this up. First thing that I'm going to do, because I mentioned that we're going to be using concentration, so we need molarities, is I need to figure out the molarities of each one of the gases that I have. So what I have is I've got 2 molarity of sulfur dioxide, and I've got 2 molarity of the nitrogen dioxide. So what I'm kind of doing here is, here's my balance reaction. I'm using this to start to set up my ICE table. So those are my initial concentrations. If you're not sure how I'm getting these initial concentrations, it's telling me the volume of the flask. Decimeters cubed is the same thing as liters, and it tells me how many moles I have of each one. So I can use that to easily calculate my molarity. So I'm going to set up my ICE table. Okay. I'm going to kind of draw some lines so you can follow where I'm putting all these different numbers. So my initial concentration is 2 molarity of both of my reactants. My initial concentrations of my products are 0, so nothing has taken place yet. What other piece of information do I have? Well, I also have that at equilibrium it was found to contain 2.6 moles of nitrogen dioxide, which means I have a concentration at equilibrium for one of my reactants, and that's 1.3 molarity. So now what I need to do is sort of fill in my other boxes. So C stands for change. How are things going to change? The reactants have to go down and the products have to go up. Well, I know that since my NO is ending at 1.3 and started at 0, that this change is 1.3. It's a 1-to-1 ratio between the sulfur trioxide and the nitrogen monoxide, so that's also a positive. This is a 1-to-1 ratio as well, so I know these two are going to be changing by the same amount. Okay, I know it's 1-to-1 because my balance reaction. E is at equilibrium. I'm going to subtract the change from the initial amount. So at equilibrium, my concentration is 0.7. This concentration is 0.7, and this concentration is 1.3. So that's how I can use this to figure out what my concentrations are. Now I need to set up my Kc expression, and I'm going to plug these numbers into my Kc expression. So to review, Kc expressions, KEQ from last year, is products over reactants. So we're going to have a concentration of products divided by my concentration of reactants, raised to whatever power, or whatever coefficient is in front of each one of the species. So everything is 1, so I don't need to worry about any exponents. And now I'm ready to just sort of plug in some numbers, and I'm getting these numbers from the equilibrium part of my table. Those concentrations are 1.3. These concentrations are 0.7. And so my value for Kc ends up being 3.45. Now let's take this opportunity to talk about units of Kc. Generally speaking, these constants are dimensionless. We could put in some units because we've got molarity times molarity divided by molarity times molarity, but they end up canceling each other out, so we don't have to worry about that so much. Usually we don't put units on Kc, but we could figure them out if we needed to. What does this value mean, 3.45? Well, this tells me that since it's greater than 1, that the reaction lies far to the right. It lies far to the product side. So it's pretty much going to completion. Not a lot of concentration of reactants when this reaction is done. Let's do another example. Okay, this time we have our value for our Kc, 1.6 times 10 to the negative fifth. That's a pretty small value, so this one is telling me that the reaction does not go that far to completion. And this time I have to figure out concentration of the products at equilibrium. So we're going to set up our ICE table to kind of organize our thoughts. I'm just going to rewrite the equation down here so you can sort of see. Okay, initial change equilibrium is what ICE stands for. NOCl, there we go. And what do I have? 1 mole of NOCl placed in a 2-liter container. So that gives me an initial concentration of 0.5 molarity. My initial concentration of this is 0, and this is 0. What I don't know is I don't have any other pieces of information other than those concentrations. So now I'm going to fill in my ICE table. Since I don't have any other additional information, I'm going to use X. I know that this is going to go down, but by how much, I don't know. So that's where I'm going to use X. Now notice my coefficient, 2. This is going to go down by 2x. This side is going to go up also by x, and since my coefficient is 2, I'm going to drop that down. The chlorine is also going to go up by x, but since it's a coefficient of 1, I'm just going to leave that as is. So that's going to be a positive x. At equilibrium, initial minus change. So 0.5 minus 2x. This is going to be 2x. This is going to be x. Now we're going to set up our Kc expression. I kind of do that off to the side. So our Kc expression is products over reactants. Notice that I'm raising this to the second power because I have 2 NOs over my reactants. And again, square it. Don't forget of the coefficients, what role that plays. And now I'm going to start plugging in my values. So this time I have an amount for the Kc, 1.6 times 10 to the negative 5. My ICE table tells me what values to plug in for NO. So it's 2x, as I figured out from my table, squared times x divided by 0.5 minus 2x, and this quantity is squared. Alright, now there's a couple different ways that we could solve this. You could use a quadratic equation to solve for x. You could use the solver function to solve for x. But I'm going to give you a little shortcut. Notice this little piece right here. We can make a pretty valid assumption. Because my Kc value is pretty small, that tells me that the reactant side is not going down by much. Generally speaking, these things are only going to be changing by less than 5%. So we can use a little shortcut that says, you know what, I'm going to ignore that 2x. I assume that it's so small that I can ignore that 2x in the denominator. So then that greatly simplifies my calculations. So I'm just going to kind of come over here so I've got a little bit more room to do my calculating. Okay. I'm going to start simplifying my expression. 2x squared times x is 4x cubed divided by that 0.5. Since I'm ignoring the minus 2x, I'm just going to go ahead and square that. That gives me 0.25. And now that looks a whole lot easier to solve. You say if you do this with a quadratic formula, you're going to come up with a pretty close answer to what I'm going to get anyway. So whatever way makes you happy. And when I go through and further simplify this expression, 4x cubed, I get 4.0 times 10 to the negative 6th. So then when I solve for x, I'm going to need to take the cube root of 1 times 10 to the negative 6th. And so my value for x is 1 times 10 to the negative 2. Now remember, one of my little hints was your value for x probably is not the answer to the question. This question says, wants to know the concentrations of the products at equilibrium. So I'm going to have to refer back to my ICE table. My final answer wants to know what is the concentration of NO. So my ICE table tells me that my concentration of NO is 2x. So now I know a value for x. So really my concentration of NO is 2 times 10 to the negative 2 molarity. My concentration of the chlorine is just x. So that concentration is 1 times 10 to the negative 2 as well. One more example. Phosphorus pentachloride. Let's try one where we've got a Kp expression instead of a Kc. See how this might be a little bit different. We have pressures. So remember, pressures are just another way of thinking about concentrations of gas. So let's get started by setting up my ICE table to see what is going to happen with my numbers. So I'm just using the balanced equation that's kind of up here. I'm just going to follow it down below. Okay, what do I have initially? Phosphorus pentachloride at an initial partial pressure of 189.2 torrs. That is my concentration. Pressures for gases, I don't have to worry about making sure that it's in ATM or anything like that. I can just go ahead and use whatever unit as long as everything is in the same unit, which tests don't usually try to mess you up that badly. My initial concentration of the PCl3 and the chlorine is 0 because the reaction hasn't taken place yet. How is this going to change? Well, the product side, or reactant side, sorry, will go down. How much, I don't know, so that's going to be X. These sides will go up by positive amounts, so we'll call those X. At equilibrium, I have 189.2 minus X, and these are positives. So now I can set up, before I get to my my KP expression, remember the idea of partial pressure, and that if we know the pressures of one of the components, we know the pressures of the other components. So we're going to have to kind of solve for X first. So to figure out my total pressure of everything is going to be the pressure of the PCl5 plus the pressure of the PCl3 plus the pressure of the Cl2. So when it says that my initial pressure is at 189.2, and I also see that at equilibrium the total pressure is 358, that gives me some more information that I can plug in and figure out what X is. So I've got my equilibrium values, minus X, okay, plus X, I'm sorry I'm running out of space here, plus X plus X. I can go ahead and simplify this equation, and I now know that my X pressure is 169.5. So I need these values in order to plug into my KP expression. So how does a KP differ from a KC? It really doesn't. It's exactly the same way. It's just set up as the pressure of the chlorine gas times the pressure of the PCl3. Doesn't matter what order we do these in, I just happen to write it that way, don't know why, divided by the pressure of the reactant, so that's the pressure of the PCl5, I'm putting those in parentheses, and now I can go ahead and plug in some numbers. So I've got 169.5 times 169.5 divided by 189.2 minus X gives me 19.7. So my KP value for this particular problem is 1,461. A huge value, which tells me this reaction is basically going to completion. Okay, we're going to wrap up this particular podcast by talking about an equilibrium constant. So if you have a set of conditions at equilibrium, if we don't have a set of conditions, rather, that are at equilibrium, how will we know which way the reaction will go? And so that's where this idea of an equilibrium reaction quotient comes in. We set up a Q expression, that's the symbol for the equilibrium quotient, exactly as you set up a K. Products over reactants, you need your balanced equation, use the coefficients as exponents, but then what you do with that value kind of depends on what your problem is looking at. If your Q is equal to K, that means your reaction is at equilibrium. So you know a K expression, or you know your K value at equilibrium. Now you've got a different set of conditions. How do you know where your reaction is compared to what is at equilibrium? So you're going to kind of compare, is my reaction going to continue towards the reverse or continue towards the forward in order to come to equilibrium? So when we compare our Q versus K values, that's what we're kind of doing here. An easy way to kind of remember is we use our little gator, and which way is the gator chomping? Which way is our product? Is our reaction going to proceed to the left, or is our reaction going to proceed to the right? So there's a few applications of this that we'll be doing in practice problems, but just keep in mind that the math is going to be exactly the same whether you have a Q quotient, a reaction quotient, or a K Q value. But really start to think about, what do these two particular numbers mean?